ኦኬ ሰላም ናችሁ? ይሰማል? ሀይ ሊማር የመጣ ልጅም አለ መሰለኝ ህፃን ልጅ። አሪፍ ነው በጣም በጊዜ ነው የጀመረው እሱ። አይሰማችሁም?
ይሰማል ዶክተር። ጉድ ሞርኒንግ።
ይሰማል ዶክተር።
ኦኬ እንጀምር። ሁላችሁም ሬዲ ናችሁ? ነው ክላስ ያሉት ጆይን አላደረጉም? Okay. Looks like you can hear me now, so we are, I think, set to go. If you guys are happy, I can probably start now. Okay, welcome to another week of our lecture. This week we talk about gravity separation. Looks like there's a few more joining, so I'll probably wait a little bit. So the past couple of weeks, I was mainly talking about the importance of mineralogy, why we need to understand mineralogy of deposits before we actually plan to process them. Because we said at the end of the day, in processing, all we do is just exploit the differences in properties of minerals in the ore. So all mineralogy does is just characterize those properties of minerals so that we have an understanding of the composition of the mineral, the physical and chemical properties of what is involved, and so on. So that's actually a very good tool to then have and then plan the processing part, okay? So that's why I was trying to emphasize importance of mineralogy in separation technologies. So one of the methods that we commonly use to beneficiate ores is gravity separation. So gravity separation, as the name implies, basically utilizes the differences in density or specific gravity of minerals. So typically, the valuable minerals tend to be denser. So for example, if you take gold ores, platinum ores, and so on, the gold or the platinum containing mineral will be heavier in comparison to the waste rock. And usually the waste rock is made from silica or silicate, and silicates tend to be lighter. So all we do in gravity separation then is we know the valuable is dense, the waste is light, so we just exploit that difference in specific gravity of the composition, the various components in the ore. But obviously, when you design an equipment for a gravity separator, there's a lot of things happening. So, for example, you would have already started with a fine material that has been ground. So it's not like you're dealing with very large rocks, you're dealing with fine particles. And those fine particles are suspended in water or some kind of media as well. So the motion and the settling will be impacted by a number of factors. So in gravity separation, when people design a gravity separator, they will consider the motion of particles inside the separator and things like that as well, in addition to, of course, the mineralogy. So I know you guys have probably talked about some of these gravity separators in the previous semester with Dr. Abubakar. So I think I've reviewed some of the material you are already familiar with. So I think when I talk about gravity separation today, I'll probably talk more about operational factors. Okay, I may not talk a lot about the equipment itself, as I think you might be already aware of most of this equipment anyway. But in any case, I might just touch on those equipments and talk about how they function or how they work. Okay, so in any case, just let me know if you have further questions or further clarifications on any of the things I'm going to discuss. Okay. So in today's lecture, we'll talk about some common gravity separation methods and also some of the basic principles involved in gravity separation. So as I mentioned, you probably are familiar with jigs, shaking concentrators, film concentrators, and centrifugal concentrators. In any case, I will touch on each of them as we go along in this lecture. So as I said, the whole point of gravity separation is we know some valuables are concentrated in the heavy part and most waste is light, possible to separate them under the influence of density or specific gravity. If you are processing coal, it's slightly different because coal is the valuable part in any coal deposit, and the coal tends to be lighter, maybe specific gravity of about 1. Okay, but in coal, typically you have ash forming minerals, and those are mainly silicates, and they would have, say, a specific gravity of somewhere around 2.5, 2.8. So the waste is actually, or the unwanted material in coal is actually denser as compared to the coal itself, which is lighter. But most other minerals, especially ore minerals, typically the valuable tends to be denser and the waste tend to be lighter. And therefore we just exploit that difference in specific gravity between the two to separate them from one another. So as I said, although density is the main parameter or the main mineral property that we're exploiting, size will obviously play a role. So for example, if particles are small but dense, and other particles are light but large, usually they have similar settling properties in gravity separators. Because although something is light, if it's large in size, it will settle at the same rate as fine but heavy particles. So again, you should consider the impact of particle size, okay? Or even whatever you have suspended the particles in. If the fluid is very thick it will limit the motion of particles, okay, in the separator. If some particles are round or some particles are flat, again, that will affect how a gravity separator will perform as well. And sometimes we talked about free and hindered settling the other day. So again, in cases where your separator is simply loaded by particles, maybe you're working at a very high percent solids, then you will have interaction between particles, and that may also limit the performance of a gravity separator as well. So as I say, although we primarily exploit differences in specific gravity or density of particles, there are also other things, operational factors and mineralogical related factors that may also impact on the performance of a given separator. Okay, so when do we typically use gravity separation? So instead of, say, other methods like flotation or magnetic separation and so on, it's mainly when other separation methods are not applicable. Okay, for example, there are cases where the ore is simply high grade and maybe you don't need to do fine grinding to liberate the target particles. So in those cases, you would do coarse grinding, particles are at reasonably large size, and therefore you can go straight ahead with gravity separation, simply because that process will be a lot more cheaper and a lot more straightforward. Okay, so partly the size, starting size, if it's somewhere around 500 micron, which is say half a millimeter size or more, typically we want to exploit the performance of a gravity separation first, because at that size, most gravity separators should function well. Okay, or maybe the ore cannot be beneficiated with, say, flotation. In flotation, as I mentioned, we mainly use surface characteristics of ores. So in this case, maybe you have the target mineral in sulfide minerals, or the target commodity like copper or gold or zinc in the sulfide mineral, which then becomes a lot more easier to float. But there are some ores where flotation is not applicable. So in those cases, maybe the option is to look for other separation methods like gravity separation. Or if you're dealing with mainly precious metals in placer deposits, for example, okay, or heavy mineral sands in beach deposits and so on, typically gravity separations perform really well simply because of that difference in density between the target and the light, and you can actually maximize the separation performance, and therefore typically you would use a gravity separator in those scenarios as well. And maybe if you have also heard about artesian mines where people go to river areas and maybe pan for gold and so on. So these are probably remote areas where individual people go out there to concentrate gold and heavy mineral ores. You could probably use simple gravity separators as well. Don't need a big construction. They can be maybe even transported from place to place very easily, as they are very small as well. You could use gravity separators in those areas as well. And therefore, again, where you use a gravity separator would depend on a number of factors. And in some cases, they work well and they're applicable. In some cases, they will be very limited, and you need to consider for other options for beneficiation. Okay, so in any case, all that we do in gravity separators is to somehow find a way of creating different settling rates for different minerals. Okay, so again, typically if specific gravity or density is the factor, we just find an optimum condition for light particles to settle at a different rate to that of heavy particles or heavy minerals. And those differences in settling rates usually depend on the density of the particles and the size of the particles. Those two, density and size of particles, will determine how fast or how slow particles settle in a separator. And those are typically related to either Stokes law or Newton's law. Again, which one of the two laws apply, whether it's the Stokes law or the Newton's law, depends on what is actually happening in the gravity separation itself. Okay, so for example, if the gravity separator involves a very slow motion of particles within its system, then you probably would have a case where Stokes law becomes the dominant one. And in this case, the terminal velocity, which I told you last time, actually is the factor that tells you how fast particles are settling. So that terminal velocity is dependent on d, which is the size of particles, and density, which is the density of the particles we're trying to separate in comparison to that of the fluid. So typically in many gravity separators, we use water as the media or as a fluid. Okay, but in any case, we can actually see how particle size d is related to the terminal velocity in those separators. In other separators where there's a lot of motion of particles in the separator, again, settling is dependent on size and density as well. But obviously those two relationships are different. Okay, so for example, in the Stokes case, particle size has a lot of impact on settling. So if there's some change in size between the particles, that will have a very significant influence on the terminal velocity as it's shown by this equation here. Okay, so the size to the power of 2 is related to that of the terminal velocity, while it's not the case. So in the case of Newton's law, it shows that if particles are given opportunity to move at a higher rate, then yes, they both depend. The settling rate depends both on size and density to a lesser extent. So in this case, you can actually even consider a couple of scenarios, okay? So if, for example, particles are not given enough time to travel in the separator, then you may not be allowing them to attain a terminal velocity, and therefore that will impact on the separation. So you may not be able to fully separate particles from one another. So again, that is some of the things that people take into consideration when designing a typical gravity separator as well. So how do we know if a gravity separator is, or gravity separation is applicable or not in a typical ore? You can actually use the so-called concentration criteria. So the concentration criteria tells you whether a gravity separation is most likely to give you benefit or not. Okay, so it is dependent on density of heavy particles minus density of the fluid divided by density of the light minus density of the fluid. So I was just telling you, say you have gold ore, okay, and the gold ore, if you did a proper mineralogical analysis, you know what is hosting the gold typically, and you can roughly also work out the density of those minerals hosting the gold. Okay, so that will give you the density of the heavy part. And as I said, typically most of the gold is anyway locked in a silicate material, or the majority of the waste is silicate material. So we know roughly, or the average density of silicate material in that ore. So typically density is somewhere around 2.5 to maybe 2.8, maybe 3 maximum. So we know roughly the density of the light. Maybe the density of the heavy is well over 10. Okay, maybe you could have 15 or whatever, somewhere there. And we know the density of the fluid, which in this case may be water. So if you know those, you can actually work out a concentration criteria. And we can do the same for other ore types, for example, for coal, for cassiterite, which is a tin ore, or hematite, or gold. You can actually work out the concentration criteria. And concentration criteria simply tells you whether separation is likely or separation is difficult, okay? Or maybe whether you need to consider a different method of separation. But in general, if the concentration criteria is more than 2.5, it actually says that, okay, gravity separation should be reasonably applied. Okay, so you should actually get a very good separation between the heavy and the light using a gravity separator. Okay, but if concentration criteria is low, so somewhere around 1.25, somewhere around there, it actually tells you that just on density alone, separation might be a bit difficult. And also what happens is as the concentration criteria decreases to somewhere around 1.5 or below 1.5, it actually says you can only work with coarse particles to be able to separate one from the other. Okay, so as particles get finer and finer, separation actually becomes very difficult. So already, before you even buy a gravity separator, or before you even take a sample and try it in the lab, you could actually roughly work out whether, gravity separation is a very good way to go with or not. Okay, so this is part of the things that you can do as part of your mineralogical assessment. You say, okay, my heavy is located in this and this, and roughly this is the density. And based on that, you work out concentration criteria. And from that, you can predict. And if, for example, you get a reasonable value for concentration criteria, you could go back and say, okay, let's try if gravity separation is a feasible way of concentrating the ore. So this figure here roughly tells you what's going on. So again, the y-axis is concentration criteria and the x-axis is size. And as you can see here, as size increases, okay, gravity separator should work well, usually for coarse particles. But as size decreases, say below, someone is presenting something. Okay, I think that's better. Okay, so if you look at particles that are below 100 micron, usually gravity separators struggle with fine particles. Simply because with fine particles, the differences in density is not significant, okay, especially when it's mixed up with water and particles are moving sufficiently well in the separator. Whoopsra, I don't know what you're trying to do, but you're sharing your slide. And that's what I'm seeing here. Can you stop sharing? Okay. So below this line here, it tells us because the concentration criteria is low, gravity separators usually struggle. Above this line, you have sufficient concentration criteria and combination of size with that, which should give you reasonable separation. So for example, if I was dealing with particles that are 1 millimeter in size or 1000 microns, and I work out the concentration criteria to be somewhere around 2, okay, so around this point here, it tells me that gravity separators should work well. Okay, so if you are dealing with the same particles around 1 millimeter, but you calculate the concentration criteria to be somewhere around 1, so you'll be sitting at this point here. So it's saying that at this particle size and concentration criteria of 1, actually gravity separators may not work well. Okay, so already by looking at this graph, we can predict whether gravity separation is theoretically possible or not. So if, for example, I was dealing with particles that are around 20 micron or 30 micron, somewhere here, even though I have very high concentration criteria, it actually tells me that because particles are very fine, this is probably not applicable for gravity separation. Okay. So in general, when particles are below 75 microns, around 70, 80 microns, gravity separators struggle because particles get finer and finer, and there's no sufficient difference in settling rate between the heavy and the dense at the light at that particle size to be able to separate them from one another. So that's why we say generally gravity separators work well in coarse size range. Okay, what about if we have particles that are very fine? We should probably consider other separating method, okay, such as flotation and so on, to be able to upgrade the ore. Okay, so talking about size range and different methods for separation. Okay, for example, if you look at this graph here, the x-axis is particle size, and this one here, the vertical one, is actually showing you different methods for separation. So you could say, for example, when you deal with coarse particles, as I said, this one is size. So at large particle size, usually screening will work well. Wet screening should work really well. Okay. But as you deal with gravity separators, as I said, gravity separators can actually be applied to particles that are maybe as small as 100 micron. So somewhere between 100 micron and 1 millimeter, gravity separators should work well. So when you say gravity separators, in this case, we're talking about maybe jigs, tables, spirals, cones, slews, and so on. They work reasonably well when particles are somewhere between 100 and 500 microns, or even up to 1,000 micron. What happens if we're not that lucky, we're dealing with fine particles? Then maybe you should consider other methods. So for example, if you look at flotation is here, and flotation can be applied to finer particles. Usually below 20 microns, flotation is not also effective. Okay, because again, at 20 micron, particles are really fine to be separated by flotation. But if your particles are somewhere in the range of between 50, 70 microns to about 200 microns, flotation works really well. So already we can see by looking at some of these methods here and the more likely particle sizes that they can be used for separation, we can also determine whether those methods are actually applicable to our process. So again, as I said, to be able to determine particle size, we need to work with liberation. Okay, we need to first find the liberation size. We need to know, say, at 100 microns, what is the fraction of particles that are liberated? Okay, if say 80 or 90% of particles are liberated at 100 micron, then that is our particle size. And therefore we need to crush and grind particles to 100 micron. And now we have these particles, so we have to come up with the best separation method that enables us upgrade the ore accordingly. Okay, so obviously you can't just randomly choose particle size for the ore. Okay, so you can't just say, oh, because gravity separation works well at 300 micron, I'm going to use gravity separation for my processing. It doesn't work like that, because if at 300 micron no liberation was achieved, then there's no point for you to go there and try to process particles that are not liberated. Okay, maybe you bought the perfect gravity separator, but particles are not liberated, so gravity separation is not going to help. So that's why I always emphasize, first understand the ore, know liberation size. Once you know liberation size and characterize the ore, then depending on what is available to you, you can pick up the best separation method. Okay. Okay, so in the following slides, I will briefly talk about some of the common gravity separators. But before I do that, do you guys have any question? Any questions so far? Okay, looks like no questions, so we'll just quickly go through this. So as I was saying, in gravity separators, density is obviously the main property, but particle size is also another factor that may affect the performance of a separator. And therefore, all we do in designing these gravity separators is somehow manipulate how particles move inside the separator. So jigs, for example, are applied to coarser particle size, and they just mainly utilize the fact that you can perturb the fluidized particle layer up and down, disturb the settled particle, and through the application of pulsation and suction, you can then allow denser particles to pass through and settle, while light particles to be collected as an overflow or as a light product. Shaking usually apply to shaking tables, for example. We just apply a shaking motion to the concentrator, and then by that, we're transforming the vibration or the shaking motion to the particles, segregate them. Typically, again, dense particles will settle, lighter particles will aggregate to the top. We use water and things like that to wash off light particles. Or maybe you just pass the particles through an inclined surface, like in film concentrators. Again, dense particles settle to the bottom. They don't travel a lot of distance on the separator, while light particles will travel the furthest on the inclined surface, and then again, you can separate them from one another. Or in cases where particle size doesn't allow us to do that. For example, when we're dealing with 20 micron particles, as I said, gravity separators generally don't apply. In those cases, maybe instead of just relying on gravitational acceleration or settling, you could just apply centrifugation, where you force particles to separate from one another under the influence of centrifugation. And in that case, we'll have centrifugal separators. Okay, but don't stress, because maybe I went quickly over each of them. So I'll just talk about them in a little bit more detail, okay, in the next slides. So if you haven't caught everything that I said, don't worry too much. Okay, so jigs, I've seen, I think, information from Dr. Abubakar's lecture. So I'm not going to go into details of how jigs operate or how many different types of jigs we have and all that, but at least I'll just briefly describe how they work, okay? So in jigs, we have particles or the feed coming through, and those typically will have fine particles, large particles, dense particles, and light particles all fed to the jig. And in this case, we have a screen where particles are retained. And just on top of that screen, we have a ragging, which can then be applied. So we can apply actually the jigging action, where we push everything down, for example, in pulsation, and this bed here of particles will lift up, and therefore particles will now become loose instead of being compacted. So as we lift everything up, the bed will lift and particles will travel upwards. And as soon as you remove the pulsating by, say, suction, what then happens is particles start to fall down. When particles start to fall down, obviously the dense ones will fall first. Dense and small particles will fall quickly, and then the light particles will start to fall slowly. So again, typically what should happen is particles should segregate just based on how heavy or how light they are. So once the dense particles settle quickly first, they should hit the screen first, and therefore they should be allowed to pass through the screen, and they should be collected in the chamber and go down to the heavy section. While the light particles, now they're being perturbed, they were falling at a lower rate compared to the heavies, so they will be retained to the top. And therefore, because this is continuously being fed and continuously we're applying the suction and pulsation motions, what should happen there is continuously we should remove the light particles through a discharge, while the heavies will keep falling through the screen and be collected in this side. So at the end of the day, you should have separation based on purely density, okay? And now particle size may play a role depending on how long particles get to fall down. So in some cases, you could have large light particles to start falling at reasonable rate as well. But if you have a proper screen, that should help you with preventing those large particles from passing through as well. So usually pulses could be somewhere between 50 and 300 pulses per minute. And obviously once you apply a pulsation motion and consolidate the bed, then you lift it up again, the stratification is disturbed, and particles then will start to fall down. Again, according to the density or specific gravity, light particles fall slowly, dense particles fall quickly, and as a result of that, you should be able to bring about separation between the heavies and the lights. So obviously, when you do the jigging, so in this case, you do the pulsation and the suction, you should target particle settling rate specifically. So this is purely based on how fast or how slow particles settle. And because particles are in very close contact with each other, sometimes particles may interfere the motion of another particle. So we have what we call the case of hindered settling in jigging. And the main properties of particles are density and size, and to some extent shape will also play a role, especially when particles are flat. They tend to be aggregating towards the top, and that may actually be a factor in separating them as well. So usually we use water as a media, and therefore, unless you use something else, typically works well in water. But if you use a different media, for example, a dense media, then you should also consider the density and viscosity of the media as well. And obviously with temperature, it's to do with kinetics and how particles interact with one another. Okay, so if now you assume a typical particle settling in a jig, you could say you can work on particle acceleration, which can be given by this expression here, where dx by dt is simply the acceleration of the particle, and therefore m by the acceleration will give you the falling force, if you like, is dependent on mg, which is obviously the gravitational acceleration of particles falling, and m prime g is the gravitational acceleration of displaced fluid. So as particles fall in a fluid, obviously they have to displace some of the fluid. So the same volume of fluid will be displaced as particles fall, and also dependent on the drag of the fluid as well. But initially, so if particles are not moving or they're moving very slowly, there should be very little drag force. So you could actually maybe ignore the effect of drag force initially at very low velocities. Okay, so in that case, that equation can simplify into something like this. But again, we say particles fall due to gravitational acceleration, and as particles fall, they displace the same volume of liquid, okay, from their paths. So in this case, you could also say instead of the mass, okay, if we say mass by volume, because the volume is always the same, so m by v, m prime by v, and m by v, you actually can work in terms of density rather than mass as well. Okay, so in this case, because particle displays the same amount of volume of fluid, so fluid volume is the same as particle volume. So you could actually say acceleration is actually dependent on just density of the particles and density of the fluid they are displacing. Okay, so what this one is saying is, or this equation is saying, is initially when particles travel very slowly in a separator, what is more important is not their size. What is important is their initial acceleration based on the density. So in other words, in a separator, if particles are not moving very fast, or if particles are moving very slowly, then the impact of particle size is less and the impact of density is high, and therefore particles can be separated mainly based on density. Although there's an impact of size, mainly particles should be separated based on density. Okay, so then you can talk about how you operate a jig or how you operate a gravity separator to maximize effect of density and minimize effect of particle size. Okay, so if, for example, particles fall short distances frequently, so in this case, maybe the way you operate the jig is give quick pulsation and sanction motion, where particles are not lifted up very highly. So if you apply long strokes, obviously you will lift particles higher. But if you actually apply quick suction and pulsation motion, then distance traveled is small, and therefore acceleration becomes a lot more significant compared to terminal velocity. And so you could actually use this type of procedure to separate small heavies from large light particles, okay, by just applying a short jigging cycle. How about if particles travel longer at a higher velocity? Then it's a different story. Now, all of a sudden, in addition to density of particles, their size will become important. So not only particles fall according to the density, they also start to fall according to their size as well. And therefore, you may have issues of a situation where small, dense particles travel at the same rate as light, large particles. And again, now I want to separate small, heavy from light, large, because they have different densities, because they have different minerals. But if I'm not allowing that condition in the separator, then they will fall at the same rate and I won't be able to separate them from one another. Okay. So if we just want to maximize effect of particle size, then we could do the opposite. So I say, okay, I know there's differences in density in my particles, but maybe the difference in density is not very significant, but the difference in size is very significant between different particles. So I could say in that case, okay, I want to maximize size of particles. So I want to separate small from large. And in this case, you could actually apply slower but longer strokes during your jigging so that you allow particles to attain a terminal velocity. And then after that, you will be able to separate particles based on their size. So all I'm saying is you could actually manipulate the way you operate a jig, for example, in this case, or a gravity separator to allow different separations to be possible. Okay, I don't know, maybe whatever I'm saying doesn't make much sense to you guys. Maybe this picture may help. So let's say you have light particles that are small, heavy particles that are small, light particles that are large, and heavy particles that are large in the feed. So we just did combination, you ground particles, then you have all these different sizes and different densities of particles. Okay, so what I was saying, when you apply small, short strokes, but faster strokes, for example, in the jigging, is when we do that, we say acceleration becomes more important. So in this case, what should happen is density is what we're exploiting. So particles fall according to the density in short jigging cycle, which means small dense and large dense fall at the same rate, because mainly what is in effect here is density. While large light and small light fall also at reasonably the same rate. So in this case, then these ones will settle quick, the dense ones could settle quick, then the lighter ones will start to fall after that. So in this case, I just exploited the differences in density, separated particles from one another. So that's one way of doing it. But in cases where you allow long strokes, what should happen for the same set of particles? The heavy ones and the large ones will start to fall at a reasonable rate. So in this case, you will have the heavy falling, which is what we want, but then you will have a situation where the large one, which is light, also falls at a reasonable rate. So in this case, we'll be separating particles based on their size rather than their density. Okay, why? Because here terminal velocity becomes more significant, and therefore particle size will become more impactful, and separation will be impacted by size as well, in addition to density. Okay, so now we applied a pulsating motion, okay, and we have now dilated particles after they have been lifted off. Particles that are dense, as I said, will start to fall quicker, and then particles that are lighter will start to fall after that. But then you have a situation where as particles compact, you have these small dense particles which can actually make through their way through the voids between large particles and fall down to the bottom of the separator. Okay, so if you allow it enough time, you could actually have a scenario where the fine small ones and dense ones can actually come and settle together with the large dense particles. And if you have this scenario, we call that consolidation trickling, where at longer periods of time during the settling, if you allow enough time, those dense particles could actually make their way and be separated as well. Okay, if you keep it really, really low, then you'll have that issue of fine particles that are light also coming down and settling by filling the voids in between particles as well. Okay, so how do you then operate a jig? Obviously, when you apply a pulsation stroke, you should have now completely made the bed mobile. So in this case, you should have a scenario where all particles have been lifted up. Okay, and when you apply a suction stroke, particles should have all fall down and stratified. So those are the two scenarios. And obviously, as soon as you finish the suction motion, you apply the pulsation stroke. Okay, so and then that goes one after the other in quick succession. So you have that motion of particles doing this up and down and up and down and up and down. So how long up or how quick depends on how you want to operate the jig. Okay. So in some cases, you could, for example, allow the suction stroke to be reduced. So as soon as you apply a pulsation motion, particles have been lifted up, and then now they fall back to compact. But you can actually reduce the amount of suction applied following the pulsation by introducing what we call hatch water. So hatch water is introduced from bottom upwards, and therefore you minimize the need for more suction. So you do still little suction, but if you are aiding it with water, you don't have to apply the same amount of suction as that of the pulsation. So in this case, you could actually allow coarse particles to penetrate the bed as well and settle. And you could also minimize that effect of consolidation trickling that I was mentioning earlier. So generally speaking, how fast or how slow the suction and pulsation motion needs to be depends on, how much are you feeding the particles with. Okay, if I'm feeding it too much, if the separator is taking too much feed material or high feed rate, then you might need to apply quick motions. So again, that depends on how I want to operate, the capacity of my separator as well, and obviously the properties of the particles, their size and the density, as I was saying earlier, and also what is available to you in terms of the jig design itself. Okay, so these are some of the advantages of jigs. Obviously, these are more general, but jigs tend to be lower cost to operate and to control as well. So these are some of the advantages. They don't actually require a lot of maintenance as well. So they operate in a reasonable rate. But one of the main issues is, especially if you have a lot of particles close to the separation gravity, then you would have very poor performance. So that's one of the downsides of using jigs. So they may not give you a very accurate separation, if you like. Okay. And obviously, in terms of size, if you have very coarse particles, say beyond 200 millimeters, they may not actually work well as well. Okay, so before I go to the next one, on checking concentrators. Let's see if you guys have any question. Any question? Okay, so it's a very quiet group. So let's keep on going. So jigs, as I said, work well for fairly coarse particle sizes, and so they should be reasonably effective. But there are also other type of concentrators. For example, shaking concentrators, as probably the name implies, we apply a shaking motion or a vibrational motion into the particles. And typically the particles, for example, could be fed on a table or something like that, where we apply a motion into the table. And so with the feed, we also introduce water to help with the stratification of the particles and also to allow the particles to be dispersed on, for example, a table and so on. And again, based on how fast or how slow particles travel on the table, we can separate them from one another. So in this case, usually when particles travel on the table, dense ones settle to the bottom, while light ones aggregate to the top. And so light ones are washed off very quickly from the table, so they don't travel long on the table, while dense ones will travel the longest on the table and they will be collected at the discharge end. Okay, probably better to use this diagram here to explain what I'm talking about. So I don't know if you guys saw any of these type of tables. Let me see if I have a picture. So they look like this one. Okay. So the table has got a lot of grooves or small lines, if you like, on the surface of the table. So what happens is we feed particles from this end, particles come down here from this end, and typically we feed the particles with water. And now as particles come, they will be entering this side of the table. And these lines here are actually small grooves on the table. So as particles come here, they enter these grooves and they settle in these grooves. Okay. So, and if particles don't settle in this groove, they come to the next one, they come to the next one, and next one. So what happens is the dense particles will settle to the bottom of this groove, okay? Or we call them riffles. And the light ones are aggregated towards the top of this riffle. So then if you use wash water, as you apply wash water, the wash water goes this way, okay? So we apply it from that corner, wash water flows down this way. Okay, so what happens is the light particles which were on top of this riffle will be washed down. They come to the next one. Here we have denser particles again at the bottom, light ones at the top, then top ones which are light will be washed, and eventually light particles should come somewhere here. Okay, so light particles will be collected somewhere here, or in this case, low density particles. If they're really large, light particles, then it's easier to wash them because they roll easily. You can actually wash them very easily. And usually large, low density particles are presented to the table somewhere here. So we can collect them here. So these are typically gangue, okay, the waste rock. Particles that are light but intermediate in size will travel a little bit longer on the table. They stay a little bit longer on the table. And again, eventually they will be collected somewhere here. So these are light, intermediate particles, okay, in size. So obviously in the feed, you should have dense particles, you should have maybe somewhere intermediate. So some particles may have the valuable and the gangue together. So they're called composite particles or middlings. Okay, so the middlings are not as heavy as the target particles, and they're not as light as the gangue particles. They're somewhere intermediate. Because of that density of middlings, middlings usually report somewhere around here, while the dense but small particles are actually the ones which travel the longest on the table. And eventually, these small dense particles arrive somewhere around here on the table. Okay, so now when you look at the table and whatever is happening on the table, you should have segregation of particles happening primarily on density, but also on size. Okay, so as I say, small dense collected here. So now you have density and size playing a role, and large particles, but lighter, being collected here. So again, you have effect of density and size as well, and all other particles somewhere in the middle, and therefore particles are being separated based on size and density. Okay, so just on what I have explained. So if you look at a table, this is one of the plants not far from here. They process tantalite ore and lithium ore, spodumene, and they use shaking tables for concentration. So feed comes somewhere here. So that's where the feed end is. And therefore particles are fed from here and they travel on the table in this direction. So if you see, these are the grooves I was talking about. So eventually large particles are collected here, and intermediate or middlings are collected here. Dense particles are collected here. And this is where the wash water is coming from. So this line here is where the wash water is supplied. So eventually I will collect my concentrate. If you look here, there's a launder here where you can use to collect the concentrates. And here we have also other collecting points where you can collect the intermediate or the middling. And that's where we collect the gangue particles. So obviously I would want to collect this one. So this is my product. This is my waste. But for the middling, because it contains some amount of valuable, maybe you can decide to recycle it back. So collect the middling, put it back through the table and see if you can further upgrade it. And typically you could use something like that for upgrading. And obviously you could have a number of these tables operating in close proximity with one another. Okay, so I talked to you about the riffles on the table. So what are they? As I said, they're simply grooves. And in the riffles, what should happen is now when I feed particles on the table, dense particles are located to the bottom of that riffle. Okay, so dense small settle first, and then dense large, and then small light, and then large light particles. So that's why when you apply wash water against this, that's why we can quickly wash off the light particles. Okay, large light particles are easily washed off, and that's why they quickly report to the close end of the table. So that's why they come in quickly, while the dense ones, because they have already settled to the bottom, they have to travel all the way to the other end of the table to be collected. Okay, so that's typically what segregation should look like inside the riffle. Okay, so how do you operate a typical shaking table or Whiffley table or whatever machine you have, which is a table concentrator? A number of factors. Some of them are dependent on the equipment itself. Some of them depends on how you operate. So for example, when you buy the shaking table, already its shape may already be fixed. The size of it is already fixed. How deep the riffle itself is already fixed. So it's already designed when you buy it. So those are what we call non-operational factors, factors that don't depend on the way you operate the table, while other factors actually are operational factors, which you can easily adjust, okay? And therefore, by adjusting those factors, you can maximize the performance of the table. Actually, table operation is trial and error. So even if you read the manual of the machine that you bought, for the particular ore you are processing, it's always a trial and error. So you have to do the tabling many times, repeat it and repeat it until you come up with the desired product. Once you get to the desired product, then you can then say, I have optimized the table. This is my operating conditions. So until you get to that desired performance, you have to probably do a lot of tests and optimize it to get an optimum performance. But in any case, I will just mention each of these quickly and how they may impact the performance of a table. So how does particle shape affect performance? That's mainly because of the fact that round particles, for example, roll very easily. Okay, so if they roll very easily, it means wash water can easily wash them down and send them to the tailing or the waste portion. So in this case, if I have my target particles, which are round, I may actually lose them to the tailing simply because water can easily wash them to the tailing end. Okay, so that can be one issue. If I have flat particles don't roll very easily on the table. So even if I apply wash water, because they're not really rolling nicely, even though they're light and gang, they may go all the way to the concentrate end where I should only get the heavy part. So again, shape alone may not be the only factor, but it can play a role in affecting the performance of a tabling operation. So again, you need to keep an eye on what's going on and maybe take sample from the tailing and see if you are getting your target particles reporting there. Okay, and if there are a lot of valuable particles in the waste, then maybe it's to do with the way you are operating the table. Maybe minimize the amount of wash water you are applying, okay, and so on, to minimize having the target particles in the tails. In terms of size, again, usually when we talk about size, it's the size range we are emphasizing on. For example, when my feed contains a very wide particle size range from fine particles to intermediate to large particles, so which is a very wide range, it actually is very difficult to optimize the tabling process. So usually narrow particle size range is what you would get an optimum performance for, and you can actually also optimize the process. So maybe if the particle size is very wide, you can maybe consider screening it first, get rid of the fine particles or get rid of the coarse particles, and then work with a narrow particle size range. And typically, if particle size is say below 50 micron, usually that's too fine for a Wiflet table anyway, or a shaking table, and therefore you should probably consider other methods instead of using a Wiflet table or a shaking table. In terms of the design of the deck itself, some are rectangular, some are diagonal. So this is just based on whatever machine you buy. And obviously when you have a diagonal deck, you actually have a larger area, you have more riffles on the table, therefore you can operate maybe at a higher capacity. And also because you have lots of grooves or riffles, particles get a lot of opportunity to be separated. So again, you may end up with a higher grade concentrate as well. Okay, so these are some of the considerations that you can look into when, for example, trying to buy a shaking table. So typically, the diagonal deck should give you a larger capacity and a higher grade in comparison to a rectangular one. But again, if that's not available to you, it's something you can consider while deciding which type of shaking table to buy. The riffle design, so this is the lines or the grooves I mentioned on the table. So again, there could be different designs, and those designs on the table depend on what quality of concentrate you want to create at the end of the day, and other factors as well. But at the end of the day, what a riffle should do on the table is at least it should be able to retain the dense particles at the bottom. And when you shake, the table is shaked, and therefore, so we are applying a stroke to the table. Table goes forward and backward, and therefore that motion should be transported and transferred to the particles, so the particles experience that shaking. If they experience that shaking, then they will segregate according to the density. If the table is not transforming that motion to the particles, then the particles won't segregate nicely, and therefore that will impact on separation. Okay, and also how deep the riffle is will also affect the segregation of particles. So if riffles are deeper, obviously it can retain more particles, okay, inside it, and it can allow for more segregation to happen or more stratification to happen, if you like. Okay, so these are some of the things that you can consider. So how deep, how long on the table, and things like that to optimize performance. So obviously, the more riffle you have on the table, or the deeper riffle you have on the table, you should produce a higher grade concentrate because of the fact that you give particles more opportunities to stratify. Okay, so those are the factors that you may have little control on. So those are probably related to the way the table was made, but there are other factors that you can actually maybe modify or change to optimize the process. And these are what we call operational factors. For example, feed rate and water flow on the table. So as much as possible, you want to create a very uniform flow of water on the table and very uniform feed to the table. What happens if you vary the feed rate? So sometimes maybe you feed a lot of material, and then sometimes you feed less material to the table. You are actually ruining how particles spread on the table. So you should look for a very nice spread of feed material on the table so that particles segregate nicely. If some spots on the table have low amount of particles, some have large amount of particles, so you are overloading some of the riffles, but some of the riffles are not used fully, and therefore that actually affects the performance of the table. So in this case, the capacity of the table and the quality of the concentrate you get will be impacted. So as much as possible, the feed rate needs to be uniform to be able to get a uniform thickness of particles on the table, and therefore you get a uniform stratification on the in the riffles on the table, so that you maximize the performance of the table. So that's feed rate. And also, as I say, we also add wash water, and therefore how fast the water flows on the table or how slow the water flows on the table will also have factors or contributions to the overall performance of a shaking table. So again, as much as possible, there should be no dry area on the table, because water actually helps with stratification. So if water flows on the table through the riffles, that actually helps with stratification. For example, it will help remove the light particles from the riffle and transport them into the discharge end. But if you don't have water on the table, or if some spots on the table are dry, no stratification happens, and light particles are not washed out from the riffles. Again, that will have an impact on the performance of the table. So generally speaking, your wash water should be somewhere around 25% of the total water used, and your feed should contain maybe somewhere around 20 to 25% solids. So the majority here is obviously water. Okay. And again, how fast water flows on the table can determine whether you get sufficient segregation and stratification in the table or not, and whether some of the light particles are washed out from the riffle and go to the discharge end or not. So those are actually very critical parameters that you need to control when operating a riffle or a Wiflet table. So another factor is, so as I said, you apply a horizontal shaking motion to the table. And obviously that means either you can move the table faster by applying higher speed strokes, or you could move the table slowly by applying longer strokes. Okay, so typically you use longer strokes to reject tailings very quickly to the discharge end. Okay, but in cases where you're dealing with fine particles, you actually apply very quick strokes at a higher speed. Actually, that helps with stratifying fine particles, while in the case of dealing with coarse particles, you apply slow strokes okay, or longer strokes. And that should help with stratification of large particles and separation of large particles. And for coal, because coal is light, usually we apply long strokes. And with that, you should be able to attain reasonable stratification for separation of coal particles from the gangue particles. Okay, another factor that you can modify, maybe when you operate a shaking table, is the inclination. So inclination is, so this is your feed end. So I feed the particles from here. And as I said earlier, dense particles are the ones coming here to this end. So when you lift this up, when you incline it, you are actually trying to make it difficult for particles to come all the way here. In other words, only the heaviest particles will be able to come to this end. All other particles will be limited from coming to the discharge end of the concentrate. And therefore, you can actually manipulate the way you operate a shaking table by simply inclining it. And inclination should usually help to, for example, produce a high quality heavy product and restrict the motion of light particles to this end of the table. Okay, so I will also have a couple of other separators I want to talk about, but before I go to the next one, is there any question on shaking table or Whifflet tables? I think they have different names. Maybe I was using Whifflet table or shaking table in particular, but you can have different names based on who made them and how they designed the riffles and so on. But the application, the way they work, everything else is pretty much the same. Okay. Any questions so far? Okay, so moving on. Another type of concentrators are flowing film concentrators. So as you can see in that picture there, so to explain this simply, you have an inclined separating plane and you feed particles from this end. And as particles travel through this incline, what should happen is heavy particles will settle to the surface of this incline and they travel only a short distance, while light particles travel the furthest on this table simply because they can be easily forced to travel along the incline, say using water. Because you usually operate particles mixed with water, the opportunity should be there for light particles to be pushed down all the way to this point on the incline, while dense particles can withstand that flow of water, and they really should travel only small distances. So then at some point, you could just collect dense particles from the surface of the incline, while light particles will simply be allowed to travel through the incline and collected at the bottom. Okay, so film concentrators are typically based on the fact that particles can travel short distances or long distances on the separating table or the separating plane based on the shape, size, and specific gravity. So as I said, if particles are light, or if they are large, or if they're round, then the chances are they will travel very far on the table and they will be collected somewhere here. If particles are small and heavy, and maybe if they're flat, then they should settle towards the bottom and they should then somehow segregate nicely like this. And therefore, if you have the correct separation points, you should be able to separate lights from heavy. So probably heard about sluice, and some places actually take small sluices to maybe river banks and so on. And in some cases where you have some free milling gold in those river banks, you could take something like this and try to concentrate gold and heavy minerals from whatever material you find around riverbanks, and sluices are very applicable for those kind of operations. Obviously, they're very simple to operate. Again, in this case, as I was saying, dense particles settle to the bottom, so you could actually put some sort of obstruction, okay, just along that inclined surface, and obviously light particles will climb up and flow to the discharge end, and dense particles should be collected somewhere at the bottom. So using this simple method, you could actually concentrate particles mainly based on gravity, although particle size may also play a role. Okay, another example of inclined surface or film concentration is, excuse me. So these are called Reichert cone or cone separator. So obviously, as you see in that picture there, you have feed coming from here, and particles are allowed to go over an inclined surface. And again, those that are denser will settle to the bottom of the inclined surface. Particles that are lighter will be retained towards the top. So what should happen is, if I have then a separating chamber here or a hole, you could actually allow dense particles to fall through that hole and be collected as a concentrate, okay, falling somewhere here, while the light particles will simply proceed to the center of this cone separator and will be subjected to further separation as they fall into the next cone. So you could actually have one cone and then another cone under it. Now the tails from this first cone will go to the next cone, and again the same process applies. You can collect further product or a middling, for example, in this case, from the first cone, and you can process this for as long as you can to be able to upgrade the material. So this is a picture of Reichert cone. I think there are about 6 of them that you can have on top of one another. So as I was saying, particles fall along the cone, and heavy particles fall to the bottom of the cone, and then there will be a cut here, as this picture shows here, where the heavies are actually collected in this box here. The light ones go to the next cone, so through this feed here, go to the next cone, and pretty much allowed to fall through incline. Slightly dense ones again will settle to the bottom of the cone and collected, while the light ones go to the next one. So you could have this kind of operation on top of one another, and you could have a number of them on top of one another, depending on how many products you want to make, and concentration can proceed reasonably well. And there are some advantages of using a Reichert cone. For example, they could operate at a higher capacity compared to many gravity separators, and they can handle very dense percent solids as well, so feed material, so up to 70% solids feed material. Okay, for example, in comparison, a shaking table may take somewhere around 20 or 25% solid. So this can handle a large percent solid or dense material being fed into them, and they can operate reasonably well. And they're also easier to operate and easier to install as well, and can be reasonably effective, and you don't need any reagents or anything to operate them. So you could also argue that they're environmentally friendly as well. But as I said, the main advantage is the fact that they could be used to operate at high percent solids, showing you large capacities of operation. So typically, if you have large plants where you process lots of material, high tonnage plant, then you could probably use something like this. Spirals are a different kind of gravity separator. Again, with spirals, as you can see in this picture on the left here, you have an inclined trough, which is rounded along a vertical axis from top to the bottom. Okay, so the inclined surface goes from top to the bottom here, and it is curved. So the way we construct the separation surface itself is curved, so it's flatter towards the center of the axis. As you go further from the axis, it is curved and curved and curved. So then what you can have is feed coming from the top and allowed to fall through an inclined surface all the way to the bottom of the spiral. Okay, so as particles travel down, obviously there will be a slight centrifugation happening because they're going in a circular motion. So there's a bit of centrifugal force playing a role as well. And obviously they go from top to bottom. So there's also gravitational acceleration, drawing them back down to the bottom of the spiral as well. Okay, so again, depending on your operation, you could have lots of spiral operating in parallel with each other to handle a large amount of material. So what is happening on the spiral lambda is that those that are very close to the axis of the spiral, okay, are shown in dark here, are actually the heavies. Why? Because as I said, particles are going down the spiral in an incline. There's a little or mild centrifugal force. This actually means that dense particles are drawn somewhere towards close to the axis, while light particles are drawn away from this spiral, okay? And we also add what we call wash water. So we also apply wash water going away from the axis, which pushes light particles away from the axis. So eventually, as particles go down the incline, you should have a situation where light particles, which are lighter here, report further away from the center of the spiral, while the dark ones here, which are the heavy, are very close to the spiral. So at the end of the day, at the bottom of the spiral, you can have openings where you collect the heavies separately, where you collect maybe the middlings or intermediate particles separately, and you collect the light particles separately as well. Maybe you would have an opportunity to put back the middlings and separate them further to be able to upgrade and recover more of the heavy from the middling as well. So again, wash water becoming important here to be able to stratify particles and allow dense particles to be collected and light particles to be rejected. Okay, so in all the separators I mentioned so far, they usually work well at coarse particle size. So when I say coarse particles, it's usually well over 100 microns, because if particles get smaller and smaller and smaller, the impact of density becomes smaller and smaller as well. And therefore, separating them just based on density or gravitational acceleration becomes a bit challenging. So in cases where you're dealing with fine particles, say below 50 micron, most of those separators I mentioned may not be applicable. So what you need is maybe a different type of concentrator. So we call them centrifugal concentrators. And in centrifugal concentrators, instead of just relying on gravitational acceleration, we also apply centrifugal acceleration. So this is to allow with separation of finer particles, okay? So typically, let's say you have particles that are around 50 micron, 40 micron, 20 micron, and so on. Those are actually fine particles. Even of those particles, unless you use something like a centrifugal concentrator, most gravity separations shouldn't even be considered because they will just give you very poor performance. But in any case, if you apply centrifugation, now you're not just relying on gravitational acceleration, you are also trying to rely on centrifugal acceleration, and you should be able to separate particles, okay, even to a very small size, to about 5 micron, okay, based on their density. And then a typical example of this type of concentrator is the Nelsar concentrator or Falcon concentrator. But both of them do very similar things. But in these separators, you actually apply what we call centrifugation. And centrifugation is applied in the bowl. For example, here is the separator for a Falcon. And inside this Falcon separator or Nelson concentrator is a ball which is rotated at a very high speed. So maybe centrifugal force could be greater than 50 times greater than the force of gravitational acceleration. So very high speed is applied, rotated, and therefore you actually create a centrifugation inside that separator. And because of that, we're not just relying on gravitational acceleration, it actually helps with separation of fine particles up as small as 5 microns, for example. Okay, and in this case, the rotation could be even up to 800 revolutions per minute. So how do they work? Typically, this work for gold ores, and they have very wide application in gold ores. In many of the places that I went to, they actually use 1 or 2 of these gravity concentrators. And typically for processes where you have fine gold and free milling, or you could use a Nelson concentrator. So as I said, inside that separator is a ball that is rotated at a very high rotation speed, and the ball itself actually got some grooves inside it. Okay, hopefully you can see those grooves from my picture there. So there are lots of lines or grooves inside it. That's actually where we trap the particles. Okay, so now feed comes from the top, feed falls here from the top, and in this case you have feed mixed with water, or particles mixed with water. And as soon as particles enter this separating chamber and this is rotated, what happens is dense particles will attain centrifugal force and they will be drawn into the grooves. So as I said, these are the riffles or the grooves inside the separator. And therefore what's happened is dense particles go and be trapped in those grooves, while light particles remain suspended in the chamber, in the separating chamber. So over time, if you run this for, usually you don't have to run it for a long time. So you could run this for maybe 10 minutes or less. Then you should have an accumulation of dense particles in those grooves. Okay. And to aid the separation and to prevent light particles from coming and also joining the heavies, what people do is also you apply what we call fluidization water. So fluidization water goes this way, and particles that are dense go this way, so opposite. So we apply a fluidization water opposite to the particles, and only the dense particles are trapped in the groove or in the riffle here. Light particles are actually washed away with water. So in other words, light particles cannot withstand the flow of water against them, and therefore they remain suspended, while dense particles will be trapped here. So after some time, you would have an accumulation of dense here and light in here. And because you're also constantly feeding, what should happen is whatever is in here in the chamber should be rejected and it will be collected, okay, as an overflow or as a discharge. And maybe after running it for a few minutes, you stop the feeding and you basically flush these dense particles out and collect them into your concentration chamber. Okay, so these usually they are semi-batch or batch operated, and therefore you feed, you apply centrifugation, separate the dense, stop the feeding, and then remove the dense that have been accumulated, wash them out, and then restart the process again. So accumulate more. After some time, you wash them off and proceed like that. And I asked the guys operating these things, and they say typically maybe you operate a lot around maybe 20-minute cycle. So one cycle will take about 20 minutes to apply the centrifugation, concentrate and fill up the grooves or the riffles, and then wash them off and back again continuously. So it's roughly somewhere around 20 minutes, 30-minute cycle. But if you have very dense particles, you could achieve stratification or separation even within 2 minutes or 3 minutes. Okay, so, but if you wanted to allow more particles to accumulate, and that could take, at least a cycle could take up to 20 minutes or so. But in any case, one of the important factors here is, as I said, the fluid water or the fluidization water to prevent light particles from coming and separating out with the dense particles. Okay, so this is just to allow only the dense particles to come and concentrate in that refill. Okay, and this is, I think I went to one of the mining sites and they were doing some maintenance, and I had a chance to take a picture of the Nelson concentrator there. So if you look at the interior of it, that's what it looks like. And hopefully you can see clearly here what we mean by the refill all around that bowl of a Nelson concentrator. Okay, so this is the separating chamber. So this is the one that is rotated at, say, 50 times that of force of gravity, and eventually dense ones trapped here, light ones will go to the overflow and they will exit the chamber through these drainage mechanisms. Okay. Okay, so I think what I will do next is maybe do a couple of exercises. Okay, just to familiarize you with the concepts in gravity separation. But before we do that, again, and you can take this opportunity to ask questions. Any questions? Okay, no questions? Then I will ask questions if you guys have no questions. Okay, so let's start with the first one. So this is just based on what I have discussed so far. Read that question and I will also play this video. Hopefully it works. Okay, maybe in this case, the situation you have is maybe your ore deposit contains obviously light and dense particles, but you want to reject light particles that are both small and large. Okay. So instead of, say, for example, trying to, in some ore deposits, the dense particles tend to be only small. So they're always going to be small particles. But in some cases, you may have particles that are dense, but they're also coarse and fine at the same time as well. So you want to capture, in some cases, dense particles, which are both light, which are both small and large. Okay, but in some operations, as I said, the only problem you have is the particles are dense and they're always small. You just want to collect them from other particles. So in this case, if you're just interested in exploiting the impact of density, okay, rather than size, and in other words, you just want to somehow find a way of negating the effect of particle size, then as I was saying earlier, you could consider operating, for example, a jig in such a way that you minimize the impact of size, but mainly exploit the impact of density. Okay, so the situation you want to create is, it's going to take a while. So the situation I want is something like this. So I know my target particles are both in fine size and in coarse size. Okay, so as I was saying, in some operations, you don't have this. So you don't have large dense particles. Maybe you have just dense particles. Okay, but in some operations or in some ores, you may not have that opportunity, but you just have dense and heavy, and the dense particles tend to be both large and small. So all I want in this situation is I want to avoid this one, the large light particles, from settling at the same way as that of the small dense particle. So I want to minimize that from happening. And to minimize that from happening, I want to exploit only density rather than size. So again, if you operate your jig using short cycles, maximize the impact of differential acceleration rather than velocity or terminal velocity, you should be able to then operate the jig in that way to maximize the effect of size rather than density. So effect of density rather than size. I think that video there is about how a jig operates. Maybe I will need to do that. So you guys can watch it in your own time, but I will just show you anyway. Okay, I think you guys can see it. Okay, so that's just a simple snapshot of how jigs work. But I think you can read about this one if you want at a later time. But in any case, operating quick cycles of jigs during pulsation and suction should give you maximum benefit of separation based on density rather than size. Okay. Now, based on what we discussed earlier, can you guys calculate the concentration criteria for this example here? So one case is where normal water is used with density of 1.05. Another example is a situation where salty water is used with density of 1.25. And you're being given density of the target, 4.2, and density of the gangue, somewhere around 2.7. So if you use that formula for concentration criteria, okay, where you say concentration criteria is equal to density of the heavy minus density of the fluid divided by density of the light minus density of the fluid. So in this case, the fluid is water and salty water. So compare concentration criteria for both and see what results you get. And then obviously based on how high the concentration criteria is, you can say one is better than the other. Okay, again, I know this shouldn't be complicated, so that's how you could probably do it. Okay, concentration criteria is given by this formula. So for water, just use density of water given there in the question. For salty water, use density of salty water. So obviously you get different values for concentration criteria. So one gives you 1.9, the other one gives you 2.03. So you could say that higher concentration criteria shows better opportunities or possibilities for gravity separation. Okay, so in this case, salty water should give you a better separation performance. Okay, just based on what's shown by the concentration criteria. Okay, and this question is talking about importance of flow rate of fluidization water. I mentioned to you fluidization water is applied against the flow of particles to restrict the segregation of fine light particles in the riffles of a Nelson concentrator. Okay, so obviously you need to get that flow rate right. If you, for example, apply only small flow rate for the fluidized water, you are actually allowing more of the light particles, and therefore that prevents some of the heavies from coming and accumulating in the riffles. If your flow rate is very high, then you're trying to prevent the heavy ones from coming and being deposited in the riffles. Again, in both cases, you will end up losing the target or the heavy particles from being collected in the riffles. Okay, so you can read about this one as well, not really complicated. Again, another question that you may ask yourself is, what are some of the advantages and disadvantages of working with different gravity concentrations? Again, I've listed here a couple of them for each of them, so you could just read through. Obviously you can add more. Okay, so this is just for exercise only. Okay, maybe let's do this one. If this is challenging for some of you, I think it shouldn't be, should still be straightforward. Okay, if you can try this. Okay, I talked to you about solid solutions last semester and how that is important in gold ores in particular. And typically, if you find gold deposits, it's very likely that you have silver with the gold, okay? So you don't naturally find 100% pure gold. Usually, even after separation and extraction, you may end up with 80% of gold and maybe up to 20% of silver. Okay, then they have to send this product to be refined further. Okay, usually people send this to a mint, and the gold mint will usually extract and separate out the silver from the gold. But in any case, if you say you have gold, 80% silver, 20%, I'm just asking you here if you can work out the typical density of that product, which is 80% silver. And we call that also electrum. Okay. So can you calculate the density of the gold with 20% silver if density of gold is given here and density of silver is given here? Obviously, these units are in kilogram per meter cube. You might be more familiar with grams per centimeter cube. So if it was grams per centimeter cube, this will be what, 19.3, and this will be 10.5. Okay, and then once you calculate this density, then the next question is, now if you had this product and this is associated with a sulfide material, which has a density of 7,500 kilograms per meter cube, then you need to discuss about the possibilities of recovering this gold from the sulfides using a gravity separator. Okay, maybe you can take water to be the media used in the gravity separation. Okay, so again, with this one, you should be able to calculate concentration criteria based on those given conditions. Okay, so then we know density is mass by volume. So in this case, for electrum or the 20% silver gold material, you should have mass of gold and mass of silver divided by volume of gold and volume of silver. So, okay, so if you say this is the sum of the masses and this is the sum of the volumes, that should give you the density. So how do you get the masses? You can maybe take, okay, so in this case, we know volume is mass by density, and instead of the volume here, you could probably use mass by density. So again, mass by density of gold and mass by density of silver. Okay, now we're being given with the densities. So we know the densities, 19,300 and 10,500. And we're told it is 20% silver and 80% gold. So if you took 100% or 100 grams or 100 kilograms or whatever of that 100, which is the sum of the gold and silver, 80 is gold and 20 is silver. So by just using those ratios, you should be able to work out the density of the electron. So in other words, a 20% silver gold should give you a density of about that. So that's actually how people also work out the quality of gold. Okay, so when we say this much carat or this much purity gold, one of the methods we use is try to work out the density of the product that we're looking at. So then if that was the product, then we say to be able to separate that type of gold from sulfides with density of that, we use the calculation of concentration criteria, density of the electron minus density of water, divided by density of the sulfide minus density of water, you get concentration criteria of 2.39. And you should be able to separate the gold from these sulfides because there's still sufficient differences in density between those two. Okay. So this I've already mentioned. Okay, and this is maybe our last exercise. Again, should be fairly easy. So you're asked to calculate mass of ferrosilicon that you would need to make up 200 in a 200 milliliter of water to make a slurry with a density of 1.5 gram per centimeter cube or 1,500 kilogram per meter cube. Okay, so you're told density of ferrosilicon is that much, and density of water, you can use about 1,000 or more accurately, say 998 kilogram per meter cube. So I will talk about ferrosilicon next week when we talk about dense media separation. But typically, if you're not using water, you could actually make up a media that's denser. And in this case, you could use ferrosilicon particles suspended in water to make up the media itself. And then you can use this separation medium to be able to, separate particles according to the gravity. So ferrosilicon or magnetite and things like that are some of the particles that we use to make up dense media for gravity separation. So in any case, if I say the density of ferrosilicon is given here, I want you to make up a density of slurry of this much, and you could use a water that's about 750 mil. How do you then calculate the mass required for ferrosilicon that you want to mix with water, 750 millimeter of water, to obtain that much? Sounds complicated, but again, it's a simple calculation. So we know density is mass by volume. So when I say density of the slurry is 1,500, so this is mass of the slurry divided by volume of the slurry. So the mass of the slurry is made from the ferrosilicon and water. So mass of water plus mass of ferrosilicon would give me mass of the slurry. And volume of the slurry is obviously volume of the ferrosilicon and volume of water. So that's just a simple calculation that you can use. So slurry density, mass of slurry by volume of slurry. And in this case, again, we just use the same concept that density is mass by volume, or mass is volume by density. So the volume I'm targeting is given here. Convert that into meter cube, and the density of water is given here. So then I calculate the mass of water in 750 mil. Then what I want to calculate is mass of ferrosilicon, but I now know mass of water. But I don't know volume of ferrosilicon, but I know the density. So if I know the density, then I can say, instead of using volume here, I'll just use mass by density of ferrosilicon. Okay, for water, I know the volume of water is already given there. So if you use the right numbers there, you should be able to also calculate mass of ferrosilicon. So in other words, if you took 0.0479 kilograms of ferrosilicon, mix that with 750 mil of water, you will get a slurry that is 1,500 kilogram per meter cube. So that's the density of that slurry. And obviously, as you can see, this slurry is denser than water. So instead of using water as a medium for gravity separation, you can use this kind of medium as a way for gravity separation. So we use something like this in dense media separation. Obviously, the media here is denser than water. Okay, I'll talk about dense media next week. Okay, so no stress about that just yet. Okay, any questions on whatever I have done? here or the previous questions or whatever I have discussed today or anything in general, please let me know. I think there's one final question here that you can probably just do it on your own. Okay, so no stress about this. But any questions so far? No question? Everything makes sense? Or doesn't make sense? Or it's all good? Or maybe you're feeling sleepy because it's just taking too long?
It's clear, doctor.
All good? Okay.
Sure.
All right. So I think it's being recorded as well, so you can watch it maybe another time again if you want. But otherwise, that should be it for today. And I will see you next week. So we'll probably just stick to the Thursdays. Is everyone happy with that?
በዚህ በአሁኑ ሰዓት ከተመቻችሁ ይሁን።
Okay. Yep.
ስለዚህ መደበኛ ሰዓት እናድርገው ማለት ነው። የሰኞ ይቅርና።
Yeah, I think so. Yeah. ስለዚህ ዝም ብለን ሐሙስ እናድርገው። I think እስካሁን ሐሙስ ኦኬ ነው ለኔ።
ሶፍት ኮፒዎቹ ቶሎ ይላኩልን።
ኦኬ፣ አሁን ሳልረሳው ልከዋለሁ። ስለዚህ መጽሐፎች እያገኛችሁ ነው?
ባለፈ አይ ያው እስከን ጀምረናል፣ ግን እንትን እያልን ነው። መጽሐፎችም ካሉ ቢላኩልን አሪፍ ሪፈረንሶች።
ኦኬ ያ። ስለዚህ ምንድነው የማደርገው? እስቲ በቅርብ ልመጣ ስለምችል ለክላስም ባይሆን የሆነ ሶፍት ኮፒ ይዤላችሁ መጣና እዛ ራሳችሁ ሼር ማድረግ ትችላላችሁ አንዳንድ መጽሐፎች።
እና ዶክተር አቡበከርን ባለፈ ያልኋችሁን ማለት እንደዚህ ፊልድ ወተን የምናያቸው ነገሮች ካሉ ከአሁኑ ኢንፎርም ተደርገውልን ክረምቱም ከመግባቱ በፊት ወተን የምናይበት ሁኔታ ቢኖር ይህንን ማየት አለባችሁ በእኔ ኮርስ የምትሉትን።
ስለዚህ መቼ ነው ሊሆን የሚችለው? ሞስት ላይክሊ ብትሄዱ መቼ ነው የምትሄዱት?
መጀመሪያ ቀኑ አይታወቅም፣ ግን ለዶክተር አቡበከር ይሄ እንዲያዩ ጥሩ ነው ምናምን የሚለውን ኢንፎርም አድርጓቸውና እኛም ኢንፎርስ እያደረግናቸው ነው እንድናይ በጀትም ስላለው የፊልድ እንትን የምናይበት ሁኔታ ቢኖር ጥሩ ነው።
ኦኬ ያ አንድ እሱ። ሁለተኛ ደግሞ የላቡንም እስቲ አሬንጅ ለማድረግ እየሞከርኩ ነው። እነግራችኋለሁ ምን ማድረግ እንደምትችሉ ለዛ። ኦኬ
እናመሰግናለን።
እሺ መልካም ውሎ።
አሜን።
ኦኬ ቻው።